Ma'am, I'm sharing the link with you.
Yeah.
Yeah, shared. Once you check, ma'am.
Yeah, I will check. I'll just check.
Yes. And I'm sharing the link with you.
Yeah.
Fine.
Yes, it's fine. It's coming. Yeah. Yeah, I've seen. Yeah, it's coming. Not a problem. Okay. Yeah, it's working fine, Suma.
Yes, ma'am.
Yes, it's fine. Let's see.
I think you will have to
Yeah,
close
I've
it,
seen.
ma'am.
Yeah, it's coming.
Ah.
I closed.
Yes, yes, yes.
It's working fine.
Yes. I think you will have to close it, ma'am.
I closed. Shall we start now, Suma?
Yes, ma'am.
Okay, you
You
start
can
then.
start. Yeah. Just a minute. Shall I start, ma'am? Am I audible?
Yes.
Yes. Yeah. Good morning to one and all present here. Mathematics is the queen of science and arithmetic the queen of mathematics. Quoted Carl Friedrich Gauss. John von Neumann said, if people do not believe that mathematics is simple, it is only because they do not realize how complicated life is. Today, 22nd of December, we all celebrate National Mathematics Day to recognize the achievements and contributions of the great Indian genius Srinivasa Ramanujan, who was born on this date in 1887. Respected dignitaries, faculty members, and my dear students, I, Suma Manjunath, from the Department of Mathematics, extend a warm welcome to you all for the webinar on the occasion of National Mathematics Day, organized by Numerano Club, Department of Mathematics, on behalf of the management of Dayanand Sagar College of Engineering. I would like to welcome today's resource person, a great orator, Professor Vittal Rao, Department of Electronic Systems Engineering, Indian Institute of Science, Bengaluru, Karnataka, to deliver a lecture on the topic Ramanujan's Mathemagic. We welcome you, sir.
Thank you.
Thank you, sir. I now request Dr. Radha Gupta, Head of the Department of Mathematics, to introduce the speaker to the audience. Over to you, ma'am.
Thank you, Suma.
Thank you.
Very good morning to Professor Vittal Rao, my dear students, the faculty of Dayanand Sagar College of Engineering. It is my privilege and honor to introduce today's speaker, Professor R. Vittal Rao. To the students, I guess students must really feel privileged to have his talk today. Professor R. Vittal Rao obtained his MSc degree in mathematics from Mysore University and his PhD degree in mathematics from Purdue University, USA. He was a faculty in the Department of Mathematics at the Indian Institute of Science, Bangalore, for more than 3 decades, and he retired in 2003 as a professor and chairman of the Department of Mathematics. Since his retirement, he has been a consultant in the Department of Electronic System Engineering, Indian Institute of Science, Bangalore. He has held positions in the Department of Civil and Hydraulic Engineering at IISc as Senior Research Assistant, also Department of Computer Science and Automation at the IISc Bangalore as Consulting Professor, and the Department of Mathematics at the IIT Madras as Senior Scientific Officer. He was also a guest faculty at the Indian Institute of Management, Bangalore. Professor Rao has held visiting professorships at Purdue University and Iowa State University in USA. He was a visiting scientist at the International Center for Theoretical Physics in Tricette, Italy. His research contributions, interests, and publications are in the areas of analysis, functional analysis, differential and integral equations, linear algebra and applications, combinatorics, signal and image processing, and general applications of mathematics to engineering problem. My dear students, this is a very, very brief introduction of Sir, and I can tell you I have been associated with him for more than 15 years, and you are getting one of the best persons to listen to today. Sir, I heartily welcome you. My students are really, I think my students, my faculty and myself, we are really privileged and honored to have you today on our online webinar. Welcome you, sir.
Thank you. So, shall I start?
Yes, sir. Please, sir.
Okay. Good morning. Thank you, Dr. Radhagupta, and all the others at the Dayanand Sagar College for inviting me here today this morning. It's been a pretty tough year for all of us with the pandemic, and I hope the year 2021 brings us all cheer and happiness. And I'm very happy that despite all these difficulties, you have arranged this program on the National Mathematics Day. I am very happy to be a part of this. First of all, I would like to make a comment about the title that I have given, Ramanujan's Mathemagics. In the year 1987, when the centenary of Ramanujan was celebrated, I think in one of the conferences in the United States, if I remember correct, it was Professor Dyson who called Ramanujan as a magical genius. And he explained, saying that an ordinary genius is one whose work, when you see, you are a little stunned, but then you feel that if I had been given enough time, maybe another 25 years, I might have also found out the same thing. But however, a magical genius is one, when you see his work, no matter how long you look at it, you simply don't figure out how he got that. And now we have 100 years today, this year, 2020, it's 100 years since Ramanujan passed away, and we have still not understood how he got many of his results. And that is why his mathematics is a kind of magic, and we call it mathemagic. Ramanujan, therefore, Dyson calls as a mathematical genius, as a magical genius. Okay, so almost everybody would have read something or the other about Ramanujan's life. They knew a few things, that he was very poor. He wrote a letter to Hardy, and Hardy got him to England, and there he flourished in his mathematics and so on. But however, I would like to begin with a quote. In the year 1986, 1 year before the birth centenary of Ramanujan, a very well-known mathematicians from the US, to whom we must be very grateful for having brought out an excellent set of volumes of edited versions of Ramanujan's notebooks. Bruce Berndt, he visited India and visited many places connected with Ramanujan's life. And after he went back, he wrote an article in the journal, The Mathematical Intelligencer. He called his visit a pilgrimage. For him, going to places connected with Ramanujan was like a pilgrimage. And in that, he wrote, I found that Ramanujan's name is known throughout India and that he is regarded almost like a saint. But his mathematics is largely unknown. With the anticipation of celebrating the centenary of Ramanujan's birth in 1987, perhaps a greater awareness of Ramanujan's contributions to mathematics can be realized, not only in his native land, but throughout the world as well. Some kind of a prophetic verse, I think it has this particular statement of his, that Ramanujan's mathematics is not that very well known in India itself, had its effect slowly but surely. Then finally, on the 125th birth centenary of Ramanujan in 2012, the Prime Minister declared his birthday, December 22nd, as the National Mathematics Day, and it is celebrated throughout the world. In fact, last night there was a beautiful talk by Professor Ken Ono. I do not know whether many of you had a chance to listen to it. In fact, there is a beautiful talk tonight by the Fields medalist Bhargava, Manjur Bhargava, tonight. It will be available on the net. I think some of you should, hopefully some of you would be able to see it. Now, because of this comment, I would therefore, instead of spending my time talking about Ramanujan's life, try to bring out some samples of Ramanujan's mathematical magic. Okay, this is only a 1 hour talk, maybe 45-50 minutes or 1 hour talk. Even after 100 years after Ramanujan's death, we have not completely understood Ramanujan. So it will be extremely difficult to make some things, many things about Ramanujan. I will just take 1 or 2 as samples of his work. Now the question arises, how does one give such a talk? There are students in the audience, there are teachers in the audience, and some of my friends, perhaps mathematics lovers and friends, enthusiasts are also logged in. I do not know. Maybe they will recording it. And so therefore, there is a heterogeneous audience. Some are very well trained, some are beginners, but some are very enthusiastic and so on. Whenever I give such a talk, there are a few advices or comments that come to my mind. One of the comments is, advice is from the very famous, one of the greatest mathematicians of all times, David Hilbert, who said that you haven't really understood a piece of mathematics until you can explain it to Mr. T.C. Mitz. This T.C. Mitz? It simply, T stands for the, C for common, then MITS, man in the street. Okay, you should be able to explain it to the common man in the street, then only you have clearly understood a piece of mathematics. But I do not think I will follow his advice for 2 reasons. I do not claim to have any great understanding of any piece of Ramanujan's mathematics still. For that is one reason. The second reason is the audience is not just the common man in the street. These are all bright students, well-trained teachers, and so on. So I just dumped Hilbert's advice, and then I look at another advice. I think it is by Ian Stewart. Some of the names maybe I would have got mixed up. I'm getting old. Okay. His advice was, damn the details, let us capture the spirit of the exercise. So certainly I will not be dwelling on details of all the mathematical technicalities, and hopefully I'll be able to capture some spirit of Ramanujan's work. Then there was a very nice advice. Again, the name I'm not very sure. Maybe most likely it is Ewing, but it may be somebody else, another editor. These are all editors of mathematical intelligence. He writes, he wrote in that article that if you go to he was talking about the United States, if you go to a good department of mathematics in any university, walk into a random room of a professor of physics and ask them, sir, I am a very naive person, I don't know anything about physics. Can you tell me what's exciting happening in physics today? Then perhaps the physics professor may start like this. Okay, you are not an expert, so let's say it's something like this. And then he may start explaining about black hole or the dark matter or something like that. Similarly, he says we go to a department of biology and randomly enter into a professor's room and ask him, so what is happening exactly in biology? I don't know anything in biology. He may say, well, so you are not an expert, so be something like this, and then he may start talking about genetics or DNA or functioning of the brain or something like that. But then when you go to a mathematician's room, a professor of mathematics, and ask him, sir, what's happening in mathematics today? I am not a mathematician. Can you explain? Then John Ewing says, it is very likely that mathematics professor will go straight to the board and say something like this: let omega BP be a probability space, or say consider X a manifold, or something like this. So then he says, why can't the mathematicians learn to say it is something like this rather than getting into technicalities right away? So my talk today will follow this advice. I will not get into technicalities. I will say it is something like this, and it will follow. I will follow half of at least the Stewart's advice. Damn the details. And hopefully, I'll keep some spirit, and I'll completely dump Hilbert's advice. And the last advice I will follow is, I won't try to say everything that Ramanujan did, because it says when you try to say everything, you end up saying nothing. So I will not be saying everything about Ramanujan's work. I hope I will be able to say something about Ramanujan's work. So with this introduction, let me begin with some comments about Ramanujan. Ramanujan initially wrote, everybody knows that Ramanujan wrote a letter to Hardy, and Hardy immediately recognized the genius in Ramanujan, called him there. But before that, Ramanujan had written to a couple of British mathematicians, Baker and Hobson. Baker and Hobson returned the papers without making any comment. Perhaps they didn't understand what was in it. And although the second person, M.J.M. Hill at the University College, commented that his papers were filled with a lot of holes, said that Ramanujan had taste of mathematics and some ability. He lacked the background and foundations to be accepted by mathematicians. He did definitely give a thorough and serious professional advice to Ramanujan's work, but refused to accept Ramanujan as a student. What a loss to Hill. Then Ramanujan wrote the first historic letter to Professor Hardy on January 16, 1913. I'll just rush through that letter and highlight one or two points. He says, I beg to introduce myself as a clerk. I am 23 years of age. I have no university education, but I have undergone ordinary school. Look at this. After leaving school, I have been employing the spare time at my disposal to work at mathematics. I have not trodden through the conventional regular course, but I am striking out a new path for myself. I have made special investigations of divergent series in general, and the results I get are termed by the local mathematicians as startling. I will skip other things. my whole he talks about something called Eulerian integrals, and then he says my whole investigations are based upon this, and I am developing these to a remarkable extent. He is so confident of his work, so much so that the local mathematicians are not able to understand me in my higher flights. And then he talks about some of Hardy's work, and then he writes a very nice sentence. I have not given the actual investigations nor the expressions that I get, but I have indicated the lines on which I proceed. Whereas he was suspicious whether if he gives all the details, maybe the other side they may publish it themselves without giving him any credit or something. So he cleverly held back the details and gave only some indications of his work. And then he says, being inexperienced, I would very highly value any advice you give me, and so on, so on his address. Of course, after a lot of reading and discussion with Littlewood, Hardy recognized that Ramanujan is indeed a genius and got him to Trinity College, where Ramanujan worked with Hardy and Ramanujan published several papers. Here are some examples of from the results, many results that Ramanujan sent to Hardy. These are all in his own handwriting. Here is one, if you look at this particular result, 1 plus 2 plus 3 plus 4, etc., equal to minus 1 over 12. This is a very interesting thing to note at. I request everyone to unmute, please. If you look at the left-hand side, you will see it is the sum of all positive numbers, and the right-hand side is a fraction and it is negative. And how did this happen? And this has a long story in itself. It has a connection with what is known as the Riemann zeta function. And he had the courage to write such a thing in a letter to Ramanujan. He was fantastic. This is a very fantastic thing that people took some time to understand what's going on. He wrote some more identities like this, very startling. These were some of the things that he wrote in his Hardy's letter. Seeing all this, Hardy said, they defeated me completely. I had never seen anything like this before. A single look at them is enough to show that they could be written only by a mathematician of the highest class. They must be true, because if they were not true, no one would have had the imagination to invent them. Okay. So such was the caliber of Ramanujan. He defeated everybody. He stunned everybody with this magic that he did. So the idea today is just to bring out one or two of this magic. Okay. Ramanujan worked in several areas. One of the areas in number theory that we deal with is called the area of arithmetical functions. What is an arithmetical function? It's a function an. So the independent variable n takes only integer value. So we have a1, a2, a3. So it's a function defined for values of n, the variable n, which is integers. So which is defined for all positive integers, and whose value, the actual value of the function need not be an integer. The independent variable is an integer, but the value of the function may not be integer. And the value can be either positive or negative integers, or real numbers or complex numbers. So it's a function whose domain is the set of all positive integers, whose value set can be either positive integers or whole integers or real numbers or complex numbers. Okay. So this is what is known as, I'll just take this definition. We can put some few extra things we want, but for us today, this is enough. Okay, some examples. Suppose I take a number n and I take the d of n to be the number of divisors that n has. For example, if n is 6, its divisors are 1, 2, 3, and 6. So d of 6 is 4. So d of n is the number of divisors that n has. Similarly, divisors of 12 are 1, 2, 3, 12, and hence d of 12 is 6. any prime number has exactly 2 divisors, and therefore d of any prime number is 2. So this function, now the domain is the integers, the value is also positive integers for this domain. Okay. Because of course Ramanujan had several such things, sigma kn. Now you take the kth powers of the divisors, take all the divisors of n and take the kth powers and add them. For example, the divisors of 6 are 1, take the 2th power, 1 squared plus 2 squared plus 3 squared plus 6. Similarly, the third power of the divisors of 12, 1 cube plus 2 cube. So these are some of the arithmetical functions. So I will now skip the other examples. These are all several examples. One of the important sums that Ramanujan gave was what is known as the Ramanujan sum, which is like this, where W is a complex primitive root of unity, and it is summed over all M, which is co-prime to Q, and you take all the powers. Okay, so I will skip this. These are all some of the examples. We can look at them leisurely. Now, what I am going to focus is there are two arithmetical functions in which Ramanujan made some phenomenal contributions. I may not be able to cover both the arithmetical functions, but at least one of them I will. The two arithmetical functions are what are known as the partition function and the Ramanujan tau function. Okay. So now I'll first discuss about the partition functions. Here, Ramanujan made some extraordinary contributions. What are partitions? Suppose I have 3 coins of 1 rupee denomination and I want to distribute them. Okay. How many ways can I distribute? So I have to make certain clarifications about this point. All the coins are alike. I cannot break the coins. It has to be given fully. I can give coins, all the coins to the same person or to different persons. The actual person is irrelevant. That I am giving it to different people is important. The order in which I distribute is not of concern. That is, if I give 3 to 1 person, 2 to 1 person A and 1 to 1 person B, that should be treated the same as 1 to A and 2 to B. The order is irrelevant. The number of ways I partition is important. For example, the partitions of 3. I can give all 3 coins to 1 person. I can give 2 coins to 1 person, a third to another. I can give 1 to each 3 persons. So there are 3 ways of partitioning the number. Let's say, for example, I have 3 coins. I give all to 1 person. Or I take the 3 coins, I put a partition there. So I get 2 coins to 1 person and 1 coin to 1 person. Or I take the 3 coins, I put 2 partitions, and I get 1 coin to 1 person, 1 coin to second person, 1 coin to third person. So these are all the ways I can partition 3, and I write P of 3 is equal to 3. In general, P of n is what you can do with n coins. How many ways I can distribute or how many ways I can split the number n, positive integer n. P of 2 is obviously there are 2 ways, and P of 1 there is only 1 coin, so you give to 1 person. So far we have P of 1 is 1, 2 coins can be distributed in 2 ways, 3 coins can be distributed in 3 ways. So what is the guess for P4? How many ways 4 coins can be distributed? Now, usually when I go to schools to talk to school students, I ask this question. Immediately there will be a number of students who will jump and give the answer. Usually this doesn't happen in colleges. In schools, these children are very happy to jump and raise their hands and give the answers. So one of the students usually will observe that the answer is 4 because P of 1 is 1, P of 2 is 2, P of 3 is 3. These are some of the answers I got in schools. One person answered, it is 5. I asked him why. He says, first one is 1, next one is 2, the third one is the sum of these two. 1 plus 2 is 3. So the next fellow must be 2 plus 3, which is 5. His argument was that. So let us see what happens to 4. We have all 4 to 1 person, put a partition, so 3 and 1, or a partition there, it give 2 and 2, or a partition there and there, so you get 2 and 1 and 1, or a partition here and partition there, so I get 1 and 1 and 1. So how many ways I got? There are 5 ways. So P of 4 is 5. So I got all these answers now. P of 1 is 1, P of 2 is 2, P of 3 is 3, P of 4 is 5. So now what is your guess for P of 5? So now as before, the previous student observed 1 plus 2 is 3, now 2 plus 3 is 5, so 3 plus 5 must be 8. So one fellow observed 8. The other guy observed, said, forget 1, then 2 is a prime number, 3 is a prime number, 5 is a prime number, so P of 5 must be the next prime number, 7, or this guy observed it must be 3 plus 5, 8. So what is it? Is it 7 or is it 8 or is it anything else? Now let's look at 5. I'll write all the partitions. I have 5, 4 and 1, 3 and 2, 3, 1, 1, 2, 2, 1, 2, 1, 1, 1 and all ones, and the number of partitions is 7. So we got P, all these answers. So what should be P6? Now the 8 guy is gone, so prime, 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 prime. So the next one must probably is a prime. So the next prime is 11. So but in between another guy came and said, sir, subsequently a odd number, odd number, odd number. So it must be the next odd number. So we again looked at the pattern and we write all the partitions of 6. These are all the partitions of 6 and it turns out to be 11, which is precisely the next prime number. So we have 1, 2, 3, 5, 7, 11. So we might probably expect P7 to be the next prime number, 13. But when we write all the partitions of 7, we get P of 7 is 15. So we didn't get the prime number also. So we have lost all the patterns. The sum part was gone, prime number part was gone, odd number part was gone. So we have P1 is 1, P2 is 2, P3 is 3, P4 is 5, P5 is 7, P6 is 11, P7 is 15. So what is the pattern? We have now lost all the pattern. In fact, it gets crazier and crazier when the number n becomes larger and larger. So let's give some examples of this partition. P of 8 is 22. The number 8 can be written as the sum of in 22 different ways. P9 is 30. P200, I don't know how many digits it has, is this much. P243 is this much. And it gets wilder and wilder and larger as we go on. So here is one example. P14031 is 92, not just 92, followed by all these numbers, followed by all these numbers, followed by all this, followed by all this, followed by all this. So it has 127 digits. Now imagine listing all of them and counting them. So now there must be some formula. Everybody thought that there must be some formula for finding it, P of n, but nobody knew how to find. So do you have any hope to get a general formula? Can I request all to mute, please? I'm getting a lot of echo. Okay, can we look for a general formula for Pn? Several attempts by mathematicians all over the world yielded no results. Then comes the magic of Ramanujan. So Ramanujan, it's called R.D. Ramanujan formula, I will tell you why, but Ramanujan gave this formula. P of n is given by this. Suddenly, from nowhere, we are dealing with whole numbers. Our answer must be a whole number. He brings in pi, he brings in g, he brings in differentiation, and all kinds of expressions there. Essentially, e to the power of pi 2 by root 3. Now, where did he get this formula? And now, if you look at this, this is his magic. He simply writes a formula, P of n. But then he puts approximately equal to. What does this sign mean? That means it is approximately equal to. So if Pn is approximately equal to that, there must be an error. So the error is what is the actual value minus the approximate value we have got. That is the error. Then of course we ask, what is the error? Then he says the error, we will call it as P2n. So therefore, he says it is approximately P to N. So the first term, it is approximately P1. The error is approximately P to N. And he gives an expression for P to N, which is similar roughly to that of P1N. Then he goes on. What about the error in the second term? Then he says the error is approximately P3N. And then he goes on, and finally he gives a series. Pn is P1N plus P2N plus P3N, etc. But the unfortunate thing is that series diverges. What does that mean? They all add up to infinity. Then how can I divide a finite number into an infinite number of ways? Then Ramanujan says, do not sum all the terms. I have just written infinite number of terms. Don't sum all of them. Take only root n terms. That means if you want P of 2000, you look at root 2000, then we get some 44 or 45. Take 44 terms and then sum all the first 44 terms, you will get the answer for P of 2000. Well, it works pretty well in the sense if you add all the 44 terms, we get a fraction. Remove the fractional part, take the whole number part, which gives the value of 2000 pretty very well. Then why is it called Ramanujan's formula, Hardy-Ramanujan's formula, when Ramanujan gave this? Well, Ramanujan did not prove, he just gave the formula, and Hardy and Ramanujan together developed a method called the circle method to prove this. And the circle method has become one of the powerful tools in number theory to prove many results even today. A small twist in the story of Ramanujan's partition function. If I showed you that Ramanujan gave the approximation as this, you see there is an exponential there. And because of this exponential, the series that they got diverged. Subsequent to Ramanujan, 17 years after Ramanujan's death, a mathematician by name Ramanujan gave a series which was a finite, which is a convergent series, and whose first term was like this. Compare this with Ramanujan's term. Essentially, it is 2 pi root 2 is pi root 2. There is an exponential here, there is a hyperbolic sign here. That is the only difference, the hyperbolic sign and the exponential. And the famous mathematician, Austrian, I guess, Atle Selberg, in one of the conferences and in one of the articles mentioned that in the summer of 1937, I had actually myself been studying this number 36, that means this partition problem of Ramanujan, and had arrived at Rademacher's formula. It always seemed strange to me why Hardy and Ramanujan did not end up with this formula. And he says, I believe firmly that the responsibility for this rests with Hardy. Why he says this? Actually, Ramanujan originally had suggested hyperbolic sign only, as Rademacher had. But in order to get the proof work, Ramanujan found to work with the exponential easier, and therefore he changed. It is said that Hardy changed the hyperbolic sign to the exponential. In fact, Ramanujan had the original correct expression with the hyperbolic sign. At the same time, we must give credit to Hardy that during that period in England, Hardy and Littlewood were the two leading mathematicians. They kind of put England on the mathematical world of the world. Hardy should get the credit for not throwing the letter that he received from Ramanujan to waste paper basket. He worked with him, he worked with Ramanujan without destroying Ramanujan's confidence. He could have easily told Ramanujan, because Ramanujan had not very formal training, he could have easily said that you don't know this, you don't know this, every undergraduate student knows this. Oh my goodness, he could have said this, you don't know this, how can you not know this? Even my undergraduate students know this. But whatever Hardy could teach, he taught him gently without destroying the genius or the confidence in Ramanujan. This is a lesson which many teachers most teachers and all teachers and mentors should learn from this entire story of Ramanujan. So that formula for the partition function is one of the magics of Ramanujan. Though Hardy proved it, though Hardy and Ramanujan have proved it using the circle method, once you know that that is the formula, it was perhaps not that difficult to devise a method to prove it. But the problem was, even today, we do not seem to understand how Ramanujan got that formula. And that's where it's magical. It is some kind of a magic from which he produced that formula. We do not understand how really he produced that formula. This is what Hardy called as absolutely natural talent. It doesn't come by teaching. It's not by formal thing. It just comes. It is natural. Okay. Ramanujan was the most talented mathematician ever in this world, as far as natural pure talent is concerned. Hardy rates mathematician. Hardy had this habit of rating mathematician, rating practically everything. He used to rate cricketers. He rated Bradman 100 and like that. So he rated natural talent among mathematicians. He gave 25 on a scale of 1 to 100 to himself. To Littlewood, one of his great companion mathematicians, British mathematicians, he gave 30 in the scale of 100. Hilbert, the greatest mathematician, probably one of the, if not the greatest mathematician of the 20th century, 80, and he gave Ramanujan 100. That shows, despite all the lack of training and all, how much Hardy respected Ramanujan and his natural talent and his magical genius. A small story before I get into the next magical thing about Ramanujan. Ramanujan in 1917, Hardy and Littlewood submitted the recommendation to get Ramanujan elected a fellow of the Trinity College. There was opposition, some of which sadly was unfortunately even racial. So it was not given. So, but in 1918, Hardy and Littlewood took the same letters and this thing and went to the Royal Society London and got him elected as the Fellow of the Royal Society London. And once, in fact, just 2 years back, in 2018, the Royal Society celebrated the centenary of Ramanujan getting elected as a Fellow of the Royal Society. In yesterday's talk, Professor Kenneth Anno was mentioning that he was a participant also there. He was one of the organizers. It's not that every day the Royal Society organizes the centenary celebrations of people getting elected as Royal Society fellows. Only very, very few have been done, like Newton, Rutherford, and so it's a great honor that they gave to Ramanujan, that they celebrated the centenary of his getting elected as a Royal Society Fellow in 2018. They celebrated the centenary. Now, once he was elected a Fellow of the Royal Society, and the Trinity College had no option, they went back to Trinity again. Now, what if somebody is a Fellow of the Royal Society? Trinity could not say no, so he was elected. The opponents were furious, they were grumbling that what a dirty trick. Okay, so now let's get back to Ramanujan's mathematics again. We talked about the partition function. Ramanujan found out some very amazing congruences. Let me explain what that means. So at the time Ramanujan worked, there was a table available for the values of Pm for n equal to 1 up to 200. That was what they were able to compute in those days. Okay, imagine 100 days there was no computer, no calculator, etc. Everything had to be done by hand. So the Pn was calculated for up to n equal to 1 up to 200, and that table was available. Now, looking at the table, Ramanujan came up with some very amazing results. So now I have shown here a table only for values up to 60. N here, Pn here, the n here, and the value of Pn here, and so on. I have given up to n equal to 60. Now, if we stare at these values on the table, we don't see anything. We see a very crazy, we don't see any pattern. You can look at it for a long time, particularly the 200, and we really don't see any pattern. But a man like Ramanujan could produce some phenomenal patterns on this. So he will now look at this table. I will now remove some entries from this table. Then he will start seeing the pattern. Now that's where the genius of Ramanujan is. So I take this table, I remove the first three, keep four. Then next remove, I go 5, 6, 7, 8, I remove. Then 10, 11, 12, 13, I remove. I keep 14. The next four I remove. I keep 19. Next four I remove. Keep 24. Keep then again next four. Keep 34, 39, 44, 49, 54, and so on. Now you see what are the numbers I am now looking at. N equal to 4, N equal to 9, N equal to 14, N equal to 19, 24. You see those N's? These N's are nothing but starting for 4, go on adding 5. 4, 9, 14, 19, 24, 29, 34, 39, 44, 49, 54, 59, and so on. These are available up to 200. What Ramanujan said was, look at these numbers. These are all numbers of the form 5k plus 4. This is 5 times 0 plus 4, 5 times 1 plus 4, 5 times 2 plus 4, 5 times 3 plus 4, and so on, 5 times 11 plus 4. So these are all numbers of the form 5k plus 4, or numbers which are n minus 4 is divisible by 5. They are written in many ways. They are n minus 4 divisible 5, or n is equal to 5k plus 4, or n is congruent to 4 mod 5. If we look at all these numbers and look at the values of Pn, they are 5, 30, 135, 490, etc. What do we see? They are all multiples of 5. They are all multiples of 5. So Ramanujan said that it doesn't matter how many values of n you calculate, this will always happen. So Ramanujan first stated that if you take a number of the form 5k plus 4, then the value of Pn is always divisible. However large k you take, that is, however large the number n you take, as long as it is of the form 5k plus 4, the number of partitions of that number will be divisible by 4, divisible by 5. Divisible by 5 is written as 0 mod 5. So this is one of the fantastic congruences that Ramanujan observed. I think from just looking at the table for 200 values, he was able to say what's going to happen far off, however far off we go, however larger values we calculate, this is going to repeat. And that's why he is sometimes referred to as the man who knew infinity. He knew exactly what's happening far off. Then, next one. Again, take this table. Let us now remove some other values now. What have I done? I have taken 5, 12, 19, 26, 33, 40, 47, 54. They are all of the form 7k plus 4, 7k plus 5. Okay. So if we take any number of the form which leaves a remainder 5 when divided by 7. So we write it as n is congruent to 5 mod 7. Whenever you take such a number, and then all the values of Pn, or if you look at the values of Pn, they're all multiples of 7, 7, 11, and then 7, 70, and so on. All these values of Pn are divisible by 7. And that's what Ramanujan observed. Whenever you take a number of the form 5 mod 7, no matter how large that n is, as long as it is 5 mod 7, the partition function will be divisible by 7. It will be 0 mod 7. I mentioned one more, third conjecture, a third focus. Now again, I'll remove a few things. I just keep 6, 17, 28, 39, 50. These are all of the form 11k plus 6. Okay. So if you take numbers of this form, the values, there are 11, 297, 3718, they are all divisible by 11. So all these numbers are divisible. If you take numbers of this form, 6 mod 11 or 11k plus 6, no matter how large n is, the Pn will always be divisible by 11. So this is the third congruence. So now let's consolidate all these congruences. The three congruences are, the first congruence, he looked at numbers of this form and he said the partition function is divisible by 5. The second congruence was numbers of this form. He said the partitions are divisible by 7. The third congruence is numbers of the form 11k plus 6, and he says it is divisible by 11. Now the questions are then in these numbers, if we see 5, 7, 11, this k multiplication was done by these 5, 7, 11, which are prime numbers, and the reminders he chose were 4, 5, 6. Okay, so in the first congruence, the prime number chosen was 5, second congruence was 7, third congruence 11. In the first case, it was divisible by 5, the same prime number he chose. The second congruence, he chose the prime number 7, the Pn was divisible by that 7. The third congruence, the prime number chose 11 and the Pn was divisible by 11. Question, why only these primes? Why not other primes? Why he chose only 5, 7 and 11? Why not other primes? And similarly, the remainders, when he chose the prime number 5, he chose 5k plus 4. Why 4? Why not 5k plus 1 or 5k plus 2 or anything like that? Now, if you look at these 4, later we realize that 24r minus 1, that is 96 minus 1, 95, is divisible by 5. Similarly, when he chose the prime number 7, he chose 5. If we choose 24r minus 1, it is 119, it is divisible by 7. And similarly, 24 times 6 minus 1 is divisible by 11. So there is some strange property with which he has chosen this remainder. So these prime numbers are chosen as 5, 7, 11, and then 5k plus r, 7k plus r, 11k plus r. These r's are chosen in a very peculiar manner such that the 24r minus 1 is divisible by that particular prime number. The question therefore is, why only these prime numbers and why only these reminders? Why not other reminders? For example, when you are taking 5, the possible reminders are, when you divide by 5, you can get 0, 1, 2, 3 or 4. These are all the reminders we can get, out of which he chose only 4. Why did he not choose 0, 1, 2 or 3? So Ramanujan's magic comes now. Ramanujan said in his paper, which you can read, it's available. It appears that there are no equally simple properties for moduli involving primes other than these three. So what he means is, this is the only choice for which you will get such divisibility property. These choice of primes and these choice of remainders are the only ones. You try whatever you want, you will not get anything else. And that is a magical thing. How he said that, what motivated him is later. Okay. Now, the fact that Ramanujan's that this was magic, it follows from the fact 72 years after Ramanujan's death, in 1992, two mathematicians proved that, well, we do not know whether Ramanujan, we cannot prove that whether Ramanujan was right in saying that these are the only primes, but we can show that if there was a prime, the r has to be chosen in such a way that this 24r minus 1 is divisible by that prime. So these two fellows said, we do not know that there are other primes for which we can get these congruences, but if there is a prime p for which we get congruence, then the remainder has to be chosen that 24r minus 1 is divisible by p. Precisely how Ramanujan chose the reminders for the cases p, 5, 7, 11, 1. For example, for p equal to 5, he could have chosen reminders 0, 1, 2, 3, 4. Out of this, only this fellow satisfies 24r minus 1 is divisible by 5, and he had exactly chosen that. And similarly, in the case of 7, the possible reminders he could have chosen are 1, 2, 3, 4, 5, 6, and out of this, only this fellow satisfies the property that 24r minus 1 is divisible by 7, and that is precisely Ramanujan chose. He took 7k plus 5 numbers. Similarly, in the case of 11, the only thing remainder that satisfies the property is 6. So he chose the numbers 11k plus 6. So Ramanujan's remainder choice was perfect. Exactly that's what is to be chosen. Then 83 years after, so what the previous two fellows showed was the Ramanujan choice of the remainder was perfect. And 83 years later, the other two mathematicians proved that the Ramanujan's choice of the prime numbers is also perfect. That 5, 7, and 11 are the only primes for which this will work. So Ramanujan had said, I do not see anything other possible, and he was right. The right primes to be chosen are 5, 7, 11, and the right remainders to be chosen are 4 for 5, and 5 for 7, and 6 for 11. So these are three magical congruences, and these were proved several years after his death. And the techniques that were used to prove these things did not even exist at the time of Ramanujan. The mathematical techniques that were developed much later, and therefore it's kind of magical how Ramanujan was so confident and precisely chose the prime numbers and precisely chose the right reminders, and said and had the confidence to say, I do not see anything else possible. That Ramanujan was right was finally proved 83 years after his death using several techniques developed after him, and which he obviously had no access to. I have maybe another 5-10 minutes, so I will not get into the second arithmetical function, the tau function, which is also a function which Ramanujan introduced in one of his papers, and he made a very beautiful conjecture in that paper about the tau function, and which was really stunning, and many people got very close to proving it, but never got to prove it. 58 years after his death, a French mathematician, Delisle, proved it, and he was given the Fields Medal. Delisle was given the Fields Medal for proving Ramanujan's conjecture on the tau function. And recently, I read an article by Professor Kumar Murthy, in which he had even brought the connection between Ramanujan's tau function and the factorization problem that today's cryptography people are interested in. But I do not have the time to go through all that. So what I'll do is I'll end up with a very small story involving Ramanujan, and which involves also brings to our mind some of our greatest mathematicians, Indian mathematicians. Here's the puzzle is not this picture. There are two great people in this picture. The person on the left is Mahalanobis, Prashant Chandra Mahalanobis, who was the founder of the Indian Statistical Institute, National Sample Surveys, the Planning Commission, etc., etc. And this is Ramanujan, whom everybody recognizes. Professor Mahalanobis had visited, was in England when Ramanujan was there at the time, working with Hardy. The story is that Mahalanobis visited Ramanujan one evening, and Ramanujan was cooking. He asked him to join him for dinner, the vegetarian dinner that Ramanujan was cooking. As Ramanujan was still cooking in the kitchen, Mahalanobis was waiting in the lounge, reading in there was a magazine called the Strand magazine, and he read a puzzle in that magazine. And then Mahalanobis probably thought that, well, Ramanujan is such a genius, let me ask him. Mahalanobis figured out a simple answer for that puzzle, so he wanted to ask Ramanujan and see whether he could answer that puzzle. And the puzzle goes like this. There is a row of houses numbered from 1 to n. So here are the houses. These houses are numbered 1, 2, 3, n. Now pick a house in the street, say house number D. Okay, so I have chosen a house which is house number D. Now, if you now look at the houses to the left of D, add all the numbers. So let's say these are all the houses which are to the left, and D plus 1 up to n are all the houses which are to the right of the house I've chosen. Now I take the sum of all the door numbers to the left of D, and I take the sum of all the numbers to the right of D. Okay, the puzzle is you have to find the number of houses, which is between 50, it is at least 50 and at most 500. The puzzle was this, but this is irrelevant. You can choose n as large as you want, and you want to choose the door number such that the number of houses to the left add up to the same thing as to the number of houses, not the number of houses, the numbers on the houses, the door numbers add up to, on the left add up to the same as the door numbers on to the right. That is, if n is equal to 8 and d equal to 6, for example, I have chosen the door number 6. The houses to the left have door numbers 1, 2, 3, 4, 5. They all add up to 15, and the houses to the right also add up to 15. Okay. So the puzzle was to find how many houses are there and which house gives you the answer that the door numbers to the left add up to the door numbers to the right. Okay, and probably the simplest one is probably Malinobis thought of this and wanted to find out whether Ramanujan finds the n as 8 and d as 6. So Ramanujan said, okay, I will give you a string of answers you write. He says, take down the solution. And he gives a series of answers. N can be 1, D can be 1, N can be 8, D can be 6, N can be 49, D can be 35, N can be 288, 204, 1681, 1189. It goes on and on and on and on. And he gives, it depends on how long the street is. If the street is long enough, 288. If the string is even long, probably you can have 1681 houses, then you choose 1189. If the street can have 9,800 houses, then choose D as 6930. Then the houses to the left, the houses to the right, door numbers add up to the same thing. Malinobis, who had thought about only 8 and 6, was stunned by that there are so many possible answers for the puzzle. He said, how did he get this? And probably Ramanujan's answer was something like this. The moment he stated the puzzle, I knew that the answer comes from a continued fraction. And then I knew exactly which, once I knew that it is a continued fraction, I knew exactly which continued fraction. I will not go into the details of the continued fraction or details of the solution, but I'll make 1 or 2 comments and conclude. It's a good exercise for you, for the students, to figure out how we could solve this problem. It's a very interesting problem. By the way, so actually this continued fraction method was due to Lagrange. Lagrange developed a continued fraction method for this problem. So let me just give you a hint. If you now try to calculate L, take a general N and a general D and calculate N and D, then you will find that you have to solve an equation of this form. 2n plus 1 whole squared minus 8d squared is equal to 1. And of course, we have one equation for finding 2 values. So for each, there will be a suitable choice of pairs of n and d, and that's what we have to find. So eventually, if you set x is equal to 2n plus 1, y equal to 3, eventually this problem boils down to solving this equation, x squared minus 2y squared is equal to 1. In general, we can look at equations as x squared minus some ky squared is equal to 1. And these are called by mistake as Pell's equation. The Pell had nothing to do with it. And Lagrange developed a continued fraction method for this. But what I want to say was, actually Brahmagupta had solved this equation. In fact, Brahmagupta and Bhaskara, they had solved this general equation, x squared minus some ky squared is equal to plus or minus 1, and even more than this, much more than the a little more general equations. And Brahmagupta developed a method called a bhavana for handling such equations. Now actually there is a journal called Bhavana. It's a very interesting journal. If you have not seen it, you can contribute to that. There are very nice articles in this. Brahmagupta developed a method called Bhavana, which is essentially the modern, what we call as binary operation. It's kind of binary operation for solutions of such equations. This was later developed by Jayadeva and Bhaskara and Narayana Pandita to solve such equations. So they can be connected to the method of continued fractions developed by Lagrange also. These are called, the method is eventually called, developed by Bhaskara and others, is called the Chakravala method. And actually, there is a small story with this. Brahmagupta had actually solved the equation x squared minus 61y squared is equal to 1. Particularly the value 61, another general equation. And we had given the solution for that equation by using his Bhavana method. And Brahmagupta was somewhere around 8th century, roughly 7th century BCE, the solution. And in the 17th century, 10 years later, the same problem that Brahmagupta had solved, x squared minus 61y squared equal to 1, was posed by Fermat, the famous number theorist, father of modern number theory. Posed that problem x squared minus 61y squared equal to 1 as a challenge problem to the European mathematicians. And he was not aware of the fact that Brahmagupta had already solved it 10 centuries earlier. So the tradition that Ramanujan is, that comes from is from a great tradition of mathematicians like Brahmagupta, Bhaskara, Aryabhatta, and others. And Ramanujan belongs to the class of modern mathematicians. Of course, this is the solutions Brahmagupta gave for plus or minus 1. And the red ones gives the solution for the equation x squared minus 2y squared equal to 1. And the blue ones, and from the red ones, we get the solutions of the problem, puzzle that Mahalanobis stated. So the genius of Ramanujan was the moment he sees a problem, somehow he saw far off, he saw all the way, all very large values of n, how it was like infinity and all, which even after 100 years, we are struggling to understand. I do not have much time to continue further. I can go on and talking, several slides there, but I will conclude by saying that one thing that I heard from one of the articles that George Andrews wrote, that is the fact that one lesson that we can learn from Ramanujan's life is that no matter how poor a background and whatever background you come from, you can achieve things far beyond the wildest dreams of anybody. And so poverty or lack of facilities is no hardship for a genius and a magical genius. And Ramanujan proved that he can produce mathematics to an extent that even after 100 years, we keep still working on his problems, and we still are trying to understand his problems. I began with the first letter of Ramanujan. I don't have the time, but I'll make one comment about the last letter of Ramanujan. Just a few days before Ramanujan died, after having returned to India from England, he wrote a letter to Hardy, which was a very small, brief letter in which he made one comment saying that I have introduced things called Mach theta functions, which arise naturally in mathematics. And then he followed it up with a certain number of identities, and nobody understood what he meant by that. First of all, nobody understood what those identities meant. And secondly, what did he mean by saying that naturally arises? We don't even understand what it is all about. And now 100 years later, we are mathematicians are now slowly getting into it. A nice thesis, PhD thesis in Netherlands, uh, opened up a few ideas and understandings of all these things. People are now working on all these Mach theta functions, I find, and they find that they're useful in very unexpected places. Yesterday, Professor Kenneth Warner was mentioning that these come out in a peculiar manner in analyzing black holes as well. So, though Ramanujan did mathematics in his own way, people are still working on it, and they're appearing in many places, like signal processing or black holes or string theory or things like that, where suddenly such applications keep coming. But Ramanujan's mathematics still stands as a magic, and there are many more magics to be opened up. And I hope the students will take this as a cue and start looking for material and read more and more about Ramanujan. And among the group of the students, eventually one or two or more Ramanujans will emerge. Thank you very much. I wish you all the luck. I now stop.
Yeah. Thank you, sir. Thank you very much, sir, for that wonderful, excellent presentation, as always expected. Any questions from students? Anybody would like to ask anything? Suma, anybody has any questions?
Yeah, students, if you have any questions, you can raise your hand so that I can unmute you. I think no.
Okay. Then I think you can thank sir.
Yeah. That was an amazing talk by Dr. Vittal Rao, sir. I would like to thank you, sir. I would like to thank on behalf of the management of Dayanand Sagar College of Engineering, principal, and the Department of Mathematics to Professor R. Vittal Rao for accepting our invitation and giving an amazing talk on Ramanujan's work. I also would like to thank the management of DSE for encouraging us to organize such webinars. I extend my gratitude to our beloved principal, Dr. CPS Prakash, for supporting this webinar. I also would like to thank the head of the Department of Mathematics, my dear colleagues and my dear students for taking part in this webinar actively. Thank you so much. The quiz link has been shared in the chat box. Students, you can answer and submit it. You will get a certificate. Also, you will know about Ramanujan. Thank you so much.
Thank you.
Thank you
Okay,
so
sir.
much, sir.
I think we can request sir. Thank you very much,
Thank
sir.
you very much.
Thank you.
Thank you.
The link has been shared. Okay, once again, I will share. Some student is asking.
You are giving them some time to complete it?
Yes, ma'am.
Okay. How much
Yeah.
time you should tell
Like
them?
20, yeah.
20
15 to
minutes.
20 minutes. Yeah, 20
Okay.
minutes I'll give.
Okay. Okay, then I will leave Suma.
Yes, ma'am. Yes, ma'am.
Yeah. Oh.
So those questions are very simple questions. You can answer.